Okay, so thank you for inviting me to talk about our project for the Atacama Large Aperture Submillimeter Telescope. So my talk today will focus mainly on the current design study, which is funded by the EU and started in March this year and will be completed in August 2024. But I have revised the talk because a little bit because so far I've been talking mostly about the plan for the design study, but today I also added some preliminary results that just came out of the antenna design work and the science study work. So here in this slide, I list the main collaborators, but there is many more of them. Okay, so motivation here, I hope to be, I will go a little bit fast. Why astronomy at submillimeter wavelengths is important. Of course, for this community, it's important for the study of star formation and planetary systems and the baryon cycle, but it is also important for many other fields in astrophysics, including cosmology, large-scale structures, and so on. What I want to point out is, which has been already highlighted in the previous talks, is why we need both single dishes and interferometers. Interferometers are very powerful follow-up machines. They produce very detailed images, high-resolution images of very narrow fields. However, they are very inefficient for blind surveys. They are very inefficient for discovering new sources, and we are all aware of that. Indeed, the most current interferometric observations with ALMA and NOEMA are basically following up sources whose positions and redshift have been unlocked with previous submillimeter surveys. Another problem of interferometers is that they're not very flexible for what concerns new instrumentation. So in order to test a new instrumentation, we always go to single dishes. So my point here is that we need the best of both worlds. So we now have these Ferraris that are ALMA and NOEMA, but we are using them to follow up the brightest, the tip of the iceberg of the submillimeter population, okay? So without a new large sensitive single dish, they will soon reach a source-starved regime. And then there is another big problem of interferometers, which is their an intrinsic limitation that we can't overcome, and it is their strong bias against extended diffuse structures. Okay, and this is a problem both related to the filtering, interferometric filtering of large-scale structures due to the lack of zero baseline visibilities, but it's also a problem of sensitivity per beam. With such small synthesized beams, in order to achieve the same sensitivity on a larger area, you need to integrate much more, and this is not often appreciated. When we quote the sensitivities of interferometric observations, even earlier for the deep field by Fabian Walter, we were quoting sensitivity per beam, but if that beam is very small, it means that on a larger, even a double size area, your sensitivity is way worse. And this is particularly problematic for some science cases, not all of them, of course, in particular for the study of large-scale interstellar medium, circumgalactic medium, and possibly intergalactic medium, observable as these wavelengths, and the study of the SZ effect. But even for very local sources like Orion, this nice work by Alvaro Acar a few years ago showed that, so he observed the Orion integral shape filament in N2H+, which is a tracer of dense gas. And with iron 30 meter, this is a band 3, okay? So in theory, you're minimizing the loss of flux. And then the same field with ALMA, very painful observation, hundreds of pointings. And ALMA is missing more than 90% of the flux, okay? And this is also affected the kinematic studies of structures. It doesn't only affect the imaging, it's also affect the spectroscopy. And this is in the best scenario, which is band 3. Okay, so then he was able to combine the data, which is not easy. I think we need more effort in single dish interferometric data combination. And he produced this beautiful map on the right. And we did a little test when we were writing science cases for AtLAST for the Astro 2020 decadal survey. And we simulated what using the adapting the CASA simulator, we simulated this structure that you see on the left, which is simply interstellar medium and circumgalactic medium in CO of a nearby star-forming galaxy. The numbers are not extremely important, but the main point is that this structure extends by, almost 100 kiloparsec on the physically. So if this galaxy is a redshift 0.02, and you ask yourself how much I would recover in 10 hours with the ACA or ALMA, the answer is posted here, and it's basically nothing. ALMA recovers the point sources. But the point here is a combination of what I was mentioning before, the filtering of large scale structure and the very low sensitivity on a large area. And here we adapted, actually Elko Van Kampen adapted the CASA simulator to reproduce a single dish observation. And we used a 50-meter single dish equipped with one ALMA receiver. So this is not even AtLAST, it's a very downgraded version of what we have in mind, and you'll recover all of it. Okay, so why we need a new large single dish? Can't we just upgrade the existing ones? Of course, upgrades on existing single dish will bring us ahead for a few years, but they will not be competitive in a time scale of 10, 20 years. And this is because of a combination of factors. The first of all is the small aperture of current submillimeter single dishes, which not only implies a small collection area, but it also implies a low spatial resolution. And this translates into confusion noise, which is what I was mentioning before. In surveys, if your submillimeter surveys, both galactic and extragalactic, are limited by confusion noise, meaning that you only get the extreme sources, okay? And this is also the reason why a large aperture single dish cannot be replaced by two smaller aperture single dishes. You really need a large diameter. Existing large aperture facilities, which were mentioned earlier by Karl, they unfortunately cannot observe high frequencies. Here I've been generous, I put 400 gigahertz, but sometimes it's even harder to observe 300. And this is due to a combination of factors. One of those is the atmosphere at the site on which they were built, but also the design and the accuracy of the dish. And there is a scientific pressure to deliver high frequency observations, okay, for several reasons, which I don't have time to go through. But and then finally, the small field of view of these single dish facilities, both the large aperture and some of the small aperture ones, means that the mapping speed is low. And there is also, we are discovering there is a very big scientific pressure to observe areas of the sky that span hundreds of degrees square, okay? So the design study for AtLAST is a 3.5 years project. The total cost is 3.5 million euros. There are 5 partners. It's led by me at the University of Oslo. And it is made of 6 main work packages. I don't think you're interested in the politics here, but if you have questions later, I'm happy to answer. So the philosophy behind our work is to be as comprehensive as possible in the design study. So we are, which is also what was requested in the call, in the European call. So we need to take into account all aspects of building a new facility. And the philosophy behind our study is that the requirements for AtLAST need to be driven by transformational science. So we stressed a lot, we asked ourselves, what is the science that we cannot do with current facilities or even reasonable upgrades of current facilities? And this is what is driving the design, which is pretty crazy, as Carl was mentioning earlier. It's absolutely crazy and difficult to achieve, but this is what we need, okay? And fortunately, we got funding, at least for the design study. So at least I am curious to see what comes out of it. So the idea is to have a 50 meter diameter single dish, non-25, with a high throughput and a field of view diameter of 2 degrees, okay? And this is explored in work package 2, which is dealing with the antenna design. Then AtLAST needs to be located at a high dry site in the Atacama Desert. We all have Chinatown in mind in order to enable observations at high frequencies. Very important, AtLAST needs to be an international partnership open to collaborations where Europe has a central role. And it needs to be a facility telescope with open time and flexibility to host and operate simultaneously multiple instruments, even in the same night, which is being explored in work package 4. And finally, we included in the design study, we involved the Department of Energy at the University of Oslo, which is exploring ways to make AtLAST fully powered by solar energy. Okay, so the antenna design is led by Tony Mroczkowski at ESO and is being conducted at the OHB Digital Connect, which is basically MT Mechatronics. This table shows the initial analysis of key requirements as it was highlighted in the AtLAST proposal. So the minimum requirement on the left and the goal requirement on the right. And I'm very happy to say that OHB has accepted as a given the first 3 requirements. So the wavelength range, which is overlapping with ALMA from 350 micron to 10 millimeters, the aperture of 50 meter and the field of view of 2 degrees. So these are taken as granted. Then we have, and indeed I put the dark symbols here. The white symbols are those that are harder to get. So the surface accuracy goal is to have a halfway front error of 20 microns, which is very, very demanding for a 50-meter dish. And we need actuators behind the dish. So just to give you an idea, this is similar to the what is requested to the ALMA antennas and 4 times better than the LMT. The problem here is gravity, but not only, it's also thermal influences and the wind. So we are trying to achieve this, but probably it will be achieved by design only at night, not during the day. Then we want to make our life more complicated, and we are including a plan for solar observations. The reason is that there is a high pressure from the solar community to make AtLAST able to observe the sun. And for us, operationally, it will also be a very good advantage because we would avoid all of the sun avoidance problems that we have in other telescopes. So if we can observe the sun, at least for a few minutes, that would be great. And elevation range actually have revised the elevation range, and now the minimum is 25 degrees rather than 20 degrees. And this is because it allows more flexibility with the structure, and also we don't have science cases that really require such a low elevation. Pointing accuracy, this is something we have been discussing offline already. The goal of 0.5 arcsecond is intended as a tracking accuracy and astronomical pointing goal. The blind mechanical pointing will be most likely something on the 2.5 arcsecond. The maximum scanning speed of 3 degrees per second has been accepted. The site also above 5,000 meters is being considered. There is not going to be enclosure. And we probably need a service tower for access to M2 and other type of operations. Okay, so the combination of this large aperture and field of view makes AtLAST really unique. And you can see it in these plots. So the plot on the left shows the primary mirror diameter. On the right, you have the corresponding angular resolution, 1.1 millimeter, as a function of year for different facilities. And to facilitate reading this plot, I plotted the names of the ones that we have been mentioning here. So the facilities shown in these plots are single dishes that can observe up to 350 gigahertz, okay? So we have, no, not 350. Well, I need to check which ones have been included, but some of these, of course, cannot observe submillimeter, real submillimeter wavelengths. But other, you know, if we were limited even further, we wouldn't have any data points on these plots. So, but here you can see AtLAST in terms of diameter is similar to the LMT, but and much better than SICAC prime, which is, you know, a cosmological survey telescope. But if you look at the middle plot, which shows the field of view as a function of year, the LMT is down here, whereas AtLAST is almost competing with the cosmology survey telescopes such as SICAC prime or Simon's Observatory. And on the right plot, you can see the throughput of AtLAST compared to all the other facilities, which is the best that you can achieve. And this large throughput means that to fill the field of view at 0.85 millimeters, you need 3 million beams. Okay. Yes, it's written here, up to 270 gigahertz. So this was the first concept that we had in the proposal for the AtLAST design. It was found by intuition from Hans Kaercher from previous projects, IRAM and LMT. This initial idea was to have an on-axis hybrid Nasmyth-Cassegrain optics with 2 Nasmyth science instruments and 1 Cassegrain instrument. But we have already progressed from this, okay? So this is not anymore our design. The reason why we progressed is because we got Richard Hills on board to do calculations for the optics. And he came up with this preferred optical layout, which is a classical Ritchey-Christian, sorry for the pronunciation, optics with the 2 mirrors, M1 and M2. M1 is 50 meter, M2 12 meters. And then there is M3, which is a flat tertiary mirror which is not participating to the optics, is not contributed to the optics, but is only deviating the beam, directing the beam to the elevation axis. And so with this design optimized using Zemax, we have 2 main features. One is that a very large focal plane, 4.6 meter diameter. And it has also significant curvature, okay? So the instruments will have to accept this and adapt to the focal plane. And the second big feature is that the diffraction limited field of view delivered by the telescope is 0.55 degrees at 0.45 millimeters and 1.4 degrees at 4 millimeters. This is what is delivered by the telescope. Of course, by including additional optics correction in the instruments themselves, or by shaping M3, you can increase a lot the diffraction limited field of view. So based on these new optics, there was a challenge that immediately questioned that preliminary design that I showed earlier. And the challenge is basically that the requirement for this 2-degree field of view really impact the sides of the optics and of the structural subsystems. And so we realized you need much more space on the rear side of the telescope, okay? So the design that I showed earlier cannot work, which is the LMT-like design. So we need to accommodate much more instruments, and what we are really stressing is that we need a lot of flexibility for operations and maintenance. And so OHB came up with a new clever design concept, which is being developed right now, and I can't show you, but will be published when before the end of the design study, of course. As a comparison here, I want to show you the difference with the LMT and the Japanese study for the LST. So the LMT has a field of view of 0.07 degrees, okay, which is 800 times smaller than AtLAST. And the Japanese study for the LST has a field of view of 0.7 degrees. So we're doing better than this, but this means that we have to abandon this design. Okay, so work package 4, how long do I have? Okay, so work package 4 is studying the operation model for AtLAST, which is very important, and it needs to give us some inputs also for the antenna design. So it is capitalizing on the experience of ALMA and ESO scientists, especially the experience gained, on Chinantor. Here I show a few pictures that show, you're familiar with the Apex control room in Sequitur and the ALMA OSF, and also one day after a snowstorm on Chinantor, what is left of the Apex observing facility. So all of these operational lessons would be included in our plan. This work will also give input, for example, regarding nighttime versus daytime observations when we're going to do the engineering work, what we're going to do with the data flow system, GTO allocation, etc., etc. And it also includes a plan to adapt existing infrastructure. So we don't want to put the cost up. So we want to use as much as possible infrastructure already in place in Chinantor. Work package 3 is studying the site, and it's taking new measurements on the site to provide the final selection for the best position for AtLAST. This is also led by Carlos de Broek at ESO and several other collaborators also from Apex. And we are considering the Chinantor area. We will consider 2 positions and take measurements with the weather tower, 50-meter tall weather tower, because we need to measure the wind profile and as well as the precipitable water vapor. And the main issue here is whether we can be either on the ALMA concession, but here there is some politics involved, or outside of the ALMA concession in the Atacama Astronomy Park. We will consider this politics, but we will mainly consider also the measurements which are taken with satellites and also on the site. So a 50-meter telescope is challenging and requires new data in order to produce a report, a recommendation report. Work package 5 is studying the energy supply for AtLAST. It's being led at the University of Oslo, and I would go quick here also because this is really outside my field of expertise. But the challenge here is to study a system, model a system that needs to operate day and night with constant power supply during 24 hours. Instruments need to remain cool, and this is something very different from all the other problems that our collaborators have faced so far. Because normally, when you plan on a hotel, then during the night you have a much lower power demand. In an observatory, it's not like that. And so this involves also a lot of research on the storage of solar energy, and the preferred solution would be a combination of a hybrid of electrochemical storage in batteries for the short term supply and storage in hydrogen for the long-term supply. And one advantage is, apart from the climate positive operation, is that it's also cost effective on the long run. Finally, science case is being investigated in work package 6. The goals is to identify the key science drivers and write the AtLAST-wide paper, produce a telescope simulator, and also the right prediction for future observations with AtLAST. I want to show you some very preliminary results from use cases submitted by the community, which we did during the summer. We got 28 use cases so far, but you're welcome to, yes, I'm out of time. You're welcome to submit more. What I want to show you here is, well, it's the request by these use cases shows a very large prevalence of heterodyne observations across the whole bands, and the workhorse bands of AtLAST appear to be band 6, 7, and 8. So there is a lot of pressure on these bands. And in Continuum is a very similar results, but there is a very strong pressure to maximize the number of pixels on the field of view. And then let me jump to my final slide. You can follow our updates on the website, and there is opportunities to collaborate. And for this specific audience, I think I would like to say we welcome collaborations with groups developing submillimeter instrumentation. We also need some input, some data, like what's going to be the size of these instruments, etc., the weight, the power consumption. And we welcome, of course, contribution for the science case. Thank you.
Thank you very much. Claudia, we have a couple of questions. So, Quentin Salomé.
Yes, well, thanks, Claudia. Claudia, it was a very interesting talk. I have two questions about this antenna. The first one is that when you have a bigger antenna, this means that the primary beam, so if you have single pixel, it's much smaller. So how will you do to reach, like, I don't remember the numbers, but it's almost square degree field of view. So how do you plan to reach such a large field of view?
With the optics and with the 12 meter secondary.
But you will have, like if you have heterodyne, if you have an heterodyne receiver, for instance, you will have a multi-pixels, or?
Yes, that's the plan. Also because one beam of AtLAST will be very small. So probably for first light instruments, we won't be able to field the entire field of view. But the idea is that from the beginning, we will have multi-pixels, you know, maybe not 1,000 pixels I was mentioning Christoph yesterday, but maybe, you know, at least half of degree of field of view or something like that.
Okay. And my second question is about the scanning speed. You mentioned like 3 degrees per second. How you will do that? Just with like moving the antenna, or also moving the optics? Because the mechanical constraint on a 15-meter antenna is quite large. So
I must admit, I'm not totally comfortable answering this question in the sense that I need to check. But okay. It's you know, it's hard to get, but it's actually not impossible, and they promised can be achieved. But of course, this is the scanning speed, not the acceleration speed. So you need to accelerate and then scan.
Okay.
But, if you want, I can check and let you know a bit, but know more about it.
Yes, please. Thank you.
Christoph?
Then about the beam sizes for the highest frequency, I think if it's 350 microns, it's if I'm not wrong, it's about 1.5 arc seconds you have power beam with. So is the pointing accuracy you mentioned sufficient for those observations? Or
yeah.
Point sources?
Yeah, that was my point, and the reply I got, and which makes sense, is that we're never gonna have one beam on the sky. So blind pointing will get you close to the center, and then with astronomical pointing, you want to put the source in the central beam. But the idea is never to have one beam, also because that's really not making the use of AtLAST field of view. So you need to, you know, your source will be in the field of view somewhere, and then you can work on the astronomical pointing model and improve that.
All right, thanks.
So I have a follow-up question on this one, and which is linked to the previous questions. It's not just a question of pointing; it's a question of tracking accuracy, and this is related to the mechanical issues. And so it would be interesting to have some requirements on the tracking. I don't think you showed.
Tracking is 0.5.
Ah, okay.
So Claudia, I just have a down-to-earth question. Do you have any idea about the cost of this telescope, and also I mean, I think that such a big telescope requires a lot of to maintain it. Is also costly, and we know that from the 30-meter and all the big dishes. So has that been considered?
Yes, but I can't tell you. But the point is that it's not that I'm mean, but really the cost is really so dependent on many choices that we make, you know. The site is so dependent on this. So I could give you a number, which is the preliminary estimate for just the antenna, but that wouldn't make any sense because it really depends on where you place it, what work you need to do on the site, what we do on the panels. If we include solar observation, then the cost for the coating and the hatching, increases a lot. So this cost would be completely relative, and instruments, we haven't even considered them. So it wouldn't make sense. But the idea is that this, we need multiple funding bodies for this. Yeah.
Okay, thank you.